Hello, and welcome to Module 5. This is called Networking and Content Delivery. This module will address the following topics. For networking, we will discuss networking basics, as well as Amazon VPC networking and security. For content distribution, we will discuss Amazon Route 53 and Amazon CloudFront. We include a demonstration that will show you how to use the VPC wizard to create a VPC with a public and a private subnet. A lab will have you use the VPC wizard to build a VPC and launch a web server. Finally, a knowledge check will be used to test your understanding of the key concepts that are covered in this module. After completing this module, you should be able to recognize the basics of networking. You should be able to describe the features of Amazon VPC and design a basic VPC architecture. Understand what are network security groups, as well as network ACLs. Identify the fundamentals of Amazon Route 53 and recognize the benefits of Amazon CloudFront. We're ready to go. Let's get started. Hello, and welcome. This video will cover basic networking concepts that will provide the necessary foundation for learning about Amazon VPC. A computer network is two or more machines that are connected together in order to communicate. A network can be logically partitioned into subnets. Networking requires a networking device such as a router or a switch. This connects all the machines together and enables communication between them. Each machine in a network has a unique Internet Protocol address assigned to it. An IP address, as it is known, is a unique number assigned to a machine in order to identify it uniquely. An IP address is similar to a phone number. It has to be unique. The IP number is expressed as a 4-decimal number separated by dots. Machines convert that decimal number to binary format in order to use it. For the IP address 192.0.2.0, each of the 4 dot-separated numbers of the address represents a maximum of 8 bits. This means that each of the 4 numbers can be anything from 0 to 255. The combined total of the 4 numbers for an IP address is 32 bits in binary format. A 32-bit IP address is called an IPv4 address. IPv6 address also exists and use 128 bits. IPv6 addresses can accommodate more user devices and were invented to compensate for the fact that IPv4 addresses are in short supply. An IPv6 address is composed of 8 groups of 4 letters and numbers that are separated by colons. Each of the 8 colon-separated groups of the IPv6 address represents 16 bits. That means each of the 8 groups can be anything from 0 to FFFF. The combined total of the 8 groups for an IPv6 address is 128 bits in binary format. A common method to describe networks and groups of IP addresses is classless interdomain routing, or CIDR. A CIDR address is expressed as an IP address, which is the first address of the network. It's followed then by a slash character. The number after the slash character tells you how many bits of the routing prefix must be steady and allocated for the network identifier. The bits that are not fixed are allowed to change. CIDR is a way to express a group of IP addresses that are consecutive to each other. In this example, the CIDR address is 192.0.2.0/24. The last number 24 tells you that the first 24 bits must be fixed. The last 8 bits are flexible, which means that 256 IP addresses are available for the network. They go in range from 192.0.2.0 all the way to 192.0.2.255. So basically, the 4th decimal digit is allowed to change from 0 to 255. The OSI model is a conceptual model that is used to explain data as it travels over a network. It consists of 7 layers and shows the common protocols and addresses that are used to send data at each layer. For example, hubs and switches work at layer 2, the data link layer. Routers work at layer 3, the network layer. The OSI model can be used to understand how communication takes place in the cloud and in basic networking. Thanks for watching. We'll see you in the next video. Welcome back. Many of the concepts of a physical network apply to cloud-based networks as well. In the cloud, much of the complexity of setting up a network has been abstracted without sacrificing control, security, and usability. This video will introduce Amazon Virtual Private Cloud, or Amazon VPC. Amazon Virtual Private Cloud is a service that lets you provision a logically isolated section of the AWS cloud called VPC. It is your very own private space in the AWS cloud. You land virtual machines and other resources inside of VPC. Amazon VPC gives you control over your virtual networking resources, including the selection of your own IP address range, the creation of subnets, the configuration of route tables, and the creation of network gateways. You can use both IPv4 and IPv6 in your VPC for secure access to resources and applications. You can also customize the network configuration for your VPC. For example, you can subdivide your VPC into subnets and create a public subnet for your web servers that can access the public internet. You can place your backend systems, such as database or application servers, in a private subnet with no public internet access at all. Finally, you can use multiple layers of security, including security groups and network access control lists, to help control access to Amazon Elastic Compute Cloud, Amazon EC2 instances in each subnet. Amazon VPC enables you to provision VPCs. A VPC is a virtual network that is logically isolated from other virtual networks in the AWS cloud. A VPC is dedicated to your account. VPCs belong to a single AWS region and can span multiple availability zones. After you create a VPC, you can divide it into one or more subnets. A subnet represents an isolated segment of your VPC with its very own range of IP addresses. Subnets belong to a single availability zone. You can create subnets in different availability zones for high availability. Subnets can be public or private. Public subnets have direct access to the internet, but private subnets do not. IP addresses enable resources in your VPC to communicate with each other, and resources over the internet as well. When you create a VPC, you assign an IPv4 CIDR block, meaning a range of private IPv4 addresses to it. After you create a VPC, you cannot change the address range, so it is important that you choose it carefully. The largest IPv4 CIDR block you can choose is /16, which gives you a total of 65,536 possible addresses. The smallest IPv4 CIDR block is /28, which gives you a total of 16 possible addresses for your VPC. It is important to remember this maximum and minimum blocks that you can actually utilize. They are hard limits, so they cannot be broken. You can associate an IPv6 CIDR block with your VPC and subnets and assign IPv6 addresses as well from that block to resources in your VPC. IPv6 CIDR blocks have a different block size limit. The CIDR block of a subnet can be the same as the CIDR block for a VPC. That means that a subnet can be as large as the entire VPC. But you can also use a subnet with its own CIDR block to subdivide your VPC. This structure enables the definition of multiple subnets. If you create more than one subnet in a VPC, the CIDR blocks of the subnets cannot overlap. You cannot have duplicate IP addresses in the same VPC. When you create a subnet, it requires its own CIDR block. For each CIDR block that you specify, AWS reserves 5 IP addresses within that block, and these addresses are not available for you to use. AWS reserves the following 5 IP addresses for different reasons. The first one is network address. The second one is for VPC local routing and internal communications. The third one is for the domain name system resolution. The fourth one is reserved for future use. And the fifth one is the network broadcast address. For example, suppose that you create a subnet with an IPv4 CIDR block of 10.0.0.0/24. This, in theory, gives you 256 total IP addresses. The subnet has 256 IP addresses, but only 251 are actually available because 5 of them are reserved by AWS. When you create a VPC, every virtual machine in that VPC gets a private IP address automatically. You can also request a public IP address to be assigned to a virtual machine when you create the instance by modifying the subnet's auto-assigned public IP address properties. An elastic IP address is a static public IPv4 address. You can associate an elastic IP address with any instance or network interface for any VPC in your account. With an elastic IP address, you can mask the failure of an instance by rapidly remapping the address to another instance in your VPC. Associating the elastic IP address with the network interface has an advantage over associating it directly with the instance. That means that you can move all of the attributes of the networking interface from one instance to another in the event of a failure in just a single step. Additional costs may apply when you use an elastic IP address, so it is important to release them when you no longer need them. An elastic network interface is a virtual network interface that you can attach or detach from an instance in a VPC. A network interface attribute follows it when it is reattached to another instance. When you move a network interface from one instance to another, network traffic is redirected to the new instance. Each instance in your VPC has a default network interface. That is called the primary network interface. It is assigned a private IPv4 address automatically, and it is within the IPv4 address range of your VPC. You cannot detach a primary network interface from an instance. You can create and attach an additional network interface to any instance in your VPC. The number of network interfaces that you can attach changes by the instance type that you're utilizing. A route table contains a set of rules called routes that directs network traffic to and from your subnet. Each route specifies a destination and a target. The destination is the CIDR block where you want traffic from your subnet to go. The target is the processing resource where the traffic is sent through. By default, every route table that you create contains a local route. This is for internal communications within the VPC. You can customize route tables by adding additional routes. You cannot delete the local route table entry. That is used for internal communications and is steady and unchangeable. Each subnet in your VPC must be associated with a route table. The main route table is the route table that is automatically assigned to your VPC. It controls the routing for all subnets that are not explicitly associated with a custom route table. A subnet can be associated with only one route table at a time, but you can associate multiple subnets to the same route table. That means that the mapping between subnets and route table is a one-to-one mapping, despite the fact that you can use the route table for multiple subnets. Thanks for watching. We'll see you in the next video. Hello, and welcome to this Academy Cloud Foundations demonstration. In this segment, we will demonstrate Amazon Virtual Private Cloud, or Amazon VPC for short. Amazon VPC lets you provision a logically isolated section of the AWS cloud where you can launch AWS resources in a virtual network that you define. So a VPC is your very own private slice of the AWS network. You have complete control over your virtual networking environment, including selection of your own IP address range, creation of subnets, and configuration of route tables and network gateways. You can use both IP version 4 and IP version 6 type addresses in your VPC for secure and easy access to resources and your applications. There are a few moving parts related to a VPC. There is also a few ways to provision and use a VPC, including an automated way that we call a VPC wizard. So, If we navigate to the VPC landing page, as we get to see here, we can examine some of the parts of a VPC like elastic IP addresses. We also get to see subnets. We also get to see routes and route tables, gateways, and a bunch of others. Please note that not all of these are required for every single implementation of a VPC. The simplest way to create a VPC takes advantage of the default VPC which already exists in each of the regions for your AWS account. We get to see on the VPC dashboard, selecting VPCs, we see what is called a default VPC. The default VPC represents prefabricated functionality so that you get to use and start experimenting with virtual machines like EC2 instances and RDS instances sooner more than later. It is also important to highlight that use of the default VPC should be considered for testing and experimentation only. In a business or a production environment situation, you want to define each and every piece of your VPC according to requirements and have them properly documented. In order for us to implement a VPC, we don't need to be networking experts. We do, however, need to be familiar with some networking fundamentals like classless inter-domain routing. Basically, this is a way to specify a group of IP addresses using a single special notation. We will see that when we configure the VPC CIDR. We also need to be familiar with the idea of an internet gateway, which is the resource to move data to and from the public internet. Finally, we need to be familiar with the idea of routes, which are the rules which dictate how traffic is going to flow into and out of our subnets. Subnets, of course, are the way that we subdivide a VPC into smaller, more usable segments. So a VPC wizard represents automation for you to define and provision frequently used VPC type configurations. In this case, we will use the Amazon VPC wizard to create a VPC, attach an internet gateway, add a subnet, and then define the routing for the VPC so that traffic can flow between the subnet and the internet gateway. So we're going to show you how to create an Amazon VPC using the wizard and explore the basic components, including public and private subnets, route tables and their route entries, NAT gateways, network ACLs, and elastic IPs. So as a first step, we will create an elastic IP address. The VPC wizard will launch a NAT gateway to provide internet access to private resources. Private resources are the type of resources that you actually land in a private subnet. These private resources basically will use the NAT gateway in order to be able to have access to the public internet. With that said, the NAT gateway will be assigned a static IP address, known as an elastic IP address. So we will create an elastic IP address now. An elastic IP address, when we select on the proper segment, is a public IPv4 address. This means that it is readable from the internet. It is a static IP address, which means that the IP address will not change. You can associate the elastic IP address with a resource in your VPC, such as a NAT gateway, as we will do, or an Amazon EC2 instance. You retain control of the elastic IP address until you release it back to AWS. So in the console, we are already on the VPC and we have selected the elastic IP address segment. We're going to click on Allocate New Address. Click on Allocate, and your elastic IP address is displayed. Once it is displayed, we click on Close, and we now have an IP address assigned to us. We now move on to create the VPC itself. We will be using the VPC wizard, which can be found by clicking on the VPC dashboard button. Notice that the VPC dashboard is the very top item on the navigation panel. If you select your VPCs, you no longer see the VPC wizards. So we're going to be selecting the VPC dashboard. The wizard automatically creates a VPC based on the parameters that you specify. Using the VPC wizard is much simpler than manually creating each component of the VPC. Until we fully understand what is going on with every piece, the wizard is the best place for us to implement a VPC. So here is a sample diagram of the VPC that we will create. We start by clicking on the VPC dashboard, and then launch the VPC wizard. When we click the Launch VPC wizard, we see a number of options here. First, we see a VPC with a single public subnet. This is basically a single public subnet connected to the internet. This is ideal for applications that operate purely in the AWS cloud. We also see, as a second option, a VPC with public and private subnets. A public subnet for internet-facing resources and a private subnet for back-end resources. A NAT gateway is also launched to provide internet access for resources in the private subnet. This is ideal for keeping private resources separate from the public internet. As a third option, we see VPC with public and private subnets on hardware VPN access. A public subnet and a private subnet are created, plus a virtual private network connection to an existing corporate data center. This is ideal when you have legacy infrastructure in a data center which can connect to the AWS cloud as combined network. Finally, we see VPC with a private subnet only on hardware VPN access. A private subnet connected to a corporate data center via a VPN connection. This is ideal for bursting into the AWS cloud to provide additional resources while remaining totally secure from the internet access. This design is often used for development and testing where no direct internet access is actually required. So we will be focusing on the second option, the VPC with public and private subnets templates. Once selected, we actually get to see a diagram of the topology that it will implement. And when we click on the select button, a number of questions need to be answered. The first one is the IPv4 CIDR block. We're going to leave that exactly as is, 10.0.0.0/16. This represents a CIDR abbreviation for over 65,000 possible IP addresses. This VPC can then be subdivided into subnets using smaller, more usable blocks from this very large pool. We're not going to be using IPv6, and for the VPC name, we're going to be using myVPC. Now notice that we have a public subnet CIDR to be able to specify. In this case, we're going to be changing the third digit to 1, leave everything else the same. The /24 AWS always reserves 5 IP address for every CIDR block that you actually define. The availability zone, we're going to select the very first one, 2A, and we're going to call it public subnet 1. Now for the private subnet, we're going to change the third digit to the number 2. That is going to be creating a different block in order to be used in this particular subnet. Notice the availability zone, I kept it the same as US West 2A, and we're going to call it private subnet 1. For NAT gateway, I'm being asked whether I have an elastic IP allocation. And in fact, this is how we started this experiment, this demonstration. So in fact, we do have an elastic IP address. In this case, we're going to be selecting it. We're not going to define any service endpoints, and we're going to leave the DNS hostnames as is. So you get to see now with the wizard, you answer only the fundamental questions related to your VPC, change the names, allocate the IP address blocks. If you already have an elastic IP, that will be automatically assigned to a NAT gateway. And all we need to do after that is create VPC. We're going to do that now and then wait for all the resources to reach a steady state. So now we get to see that the VPC resources have been successfully created. We now get to explore our VPC. So first things first, we're going to select your VPCs. Now, above and beyond the default VPC, again, that one is considered for testing and experimentation only. It represents prefabricated functionality. We also get to see myVPC, which is what we just created. When we select on the left checkbox, you get to see a description that reminds you of the IPv4 CIDR that was assigned to it. It gives you the VPC ID and a number of other configurations that have been prefabricated in order to allow us to use this VPC sooner more than later. Now, if we select on Internet Gateways all the way to the left navigation panel, we're going to be able to appreciate two of them. One of them is attached to our VPC. Let's make it visible here. The very first one is attached to my VPC. The second Internet Gateway is basically attached to the default VPC. The Internet Gateway for our VPC is clearly displayed here, so we're going to be selecting it. And an Internet Gateway basically connects your VPC to the Internet. So if the Internet Gateway was not present, then the VPC will have no connectivity at all to the public Internet. An Internet Gateway is basically a horizontally scaled, redundant, and highly available VPC component. It therefore imposes no availability risk or bandwidth constraints on your network traffic. Continue to examine our VPC, we can select on subnets. A subnet is basically a subsegment, a slice of an existing VPC. So a subnet always belongs to a specific VPC, and a subnet always exists in a single availability zone. Notice a VPC can actually span multiple availability zones, but the mapping and relationship between a subnet and an availability zone is a one-to-one mapping. A subnet always lives in a predefined specific availability zone. A subnet also has a range of IP addresses, which is usually a subset of the IP addresses that were assigned to the VPC in which it lives. So the CIDR range has already been defined for a number of subnets. We have two subnets in our VPC, and that is a public subnet as well as a private subnet. So let's select the public subnet. They actually have names, and we select public subnet 1, the way that we named it. In this subnet, the IPv4 CIDR happens to, in this particular case, be 10.0.1.0/24, giving us a potential of 251 possible IP addresses. This is because there are several reserved addresses in each subnet, and one IP address has actually been consumed by the NAT gateway. That's why we get to see 250 instead of 251. When we select the route table, we get to appreciate two local entries over here. The first one is the local route. The local route with the target local directs traffic destined for elsewhere in the VPC, so that anything that is moving within the VPC can actually communicate with each other. This traffic never leaves the VPC. The second entry that we get to see uses the CIDR abbreviation for the public internet, and in this case that is 0.0.0/0. That represents the public internet, and this particular route entry is directing all traffic to be processed by the Internet Gateway. So routing rules are evaluated from the most restrictive, with the bigger number after the slash, through the least restrictive, which is the 0.0.0/0, since it refers to the entire internet. So traffic is first sent within the VPC, and if it fails within the range of the VPC, then it gets sent to the internet. The rules can then be edited based upon your particular network configuration. The fact that this subnet is associated with a route table that has a route to an internet gateway makes it a public subnet. That is the definition of a public subnet. A public subnet is basically the sum of a VPC, an internet gateway that has been attached to the VPC, a subnet that has been defined according to the instructions that we just demonstrated, and finally, a routing table that indicates that public traffic is going to be processed by the internet gateway. We move forward examining the pieces of our VPC, and we can focus now on Network Access Control List. A Network Access Control List is an optional layer of security for your VPC that acts as a firewall for controlling traffic in and out of subnets. Network ACLs are normally left with their default settings that allow all traffic in and out of subnets. So in this case, if we select the Network Access Control List that is related to my VPC, we get to see that this is a default NACL. This is prefabricated functionality that continues to assist you in making things easier and simpler for you to implement a VPC.
Until you develop an understanding of all the different moving parts, creating these things from scratch can actually become difficult. We want to avoid that, and the wizard actually helps us be able to implement a well-defined, usable VPC. So we have the NACL properly defined. On the inbound rule, we get to see that Rule 100 for inbound allows all inbound traffic into the public subnet. The Rule 100 for outbound allows all traffic out of the public subnet. The second line in each of these rule sets, notice, has an asterisk, and this basically acts as a catch-all rule. In case traffic does not match any of the numbered rules, then this particular rule will be applied. And notice how it's actually denied for any case that traps it. We now go back to subnets, and when we select the private subnet, we get to examine again the IP addresses. In this case, notice 251, because the private subnet doesn't have any resources allocated to it. The public subnet did have a resource allocated to it, and that is the NAT gateway. The private subnet, in this case, is empty. And if we select the route table for the private subnet, we get to see again the local route that is taking care of having communicate all of the resources within the VPC, be able to connect and communicate with one another. However, notice that the public CIDR 0.0.0.0/0 is now being processed by the NAT gateway instance. This is a way to create a one-way street from the private subnet to the public internet. And the NAT gateway provides this traffic in order for us to be able to implement patching and updates of resources within the private subnet. The network ACL for that subnet is configured exactly the same as the other one. The default network ACL usually is wide open. We have the idea of a security group that actually applies to EC2 instances, as it will be case on the Elastic Container Service, as it is the case of actual EC2 instance, as it is the case on relational database services. And then the security groups actually act as another layer of protection, acting as a firewall. So by default, the network ACLs that are prefabricated when we provision an infrastructure like this VPC are actually open. However, that gives us then security groups for us to protect the traffic in and out of actual resources that exist. Last but not least, we go back to our VPCs and we get to appreciate the VPC that we just created. The idea of tags represents the markings that we establish in terms of name, key, and value pairs. And VPC flow logs are basically the logging mechanism that captures all of the traffic related that is moving in and out of this VPC or a particular subnet or a particular network interface. So going back to the dashboard, we get to see the landing panel and the Launch VPC wizard. This completes this Amazon VPC Cloud Foundations demonstration. Thanks for watching.
Welcome. Welcome. Now that you have learned about the basic components of a VPC, you can start routing traffic in interesting ways. In this section, you will learn about VPC networking options. An internet gateway is a scalable, redundant, and highly available VPC component that allows communication between instances in your VPC and the public internet. An internet gateway serves two purposes. Number one, to provide a target in your VPC route tables for internet traffic. And number two, to perform network address translation for instances that were assigned public IPv4 addresses. To make a subnet public, you attach an internet gateway to your VPC and add a route entry to the route table associated with the subnet. A network address translation, or NAT gateway, enables instances in a private subnet to connect to the internet or other AWS services, but it prevents the public internet from initiating a connection with those instances. To create a NAT gateway, you must specify the public subnet in which the NAT gateway should live. You must also specify an elastic IP address to associate with the NAT gateway when you create it. After you create a NAT gateway, you must update the route table that is associated with one or more of your private subnets to point internet-bound traffic to the NAT gateway. This will allow instances in your private subnets to communicate with the internet. You can also use a NAT instance in a public subnet in your VPC instead of a NAT gateway. However, AWS recommends that you use a NAT gateway instead of a NAT instance because a NAT gateway is a managed service that provides better availability, higher bandwidth, and less administrative effort. VPC sharing enables customers to share subnets with other AWS accounts in the same organization. VPC sharing enables multiple AWS accounts to create their application resources, such as Amazon EC2 instances, Amazon Relational Database Services, Amazon Redshift clusters, and AWS Lambda functions into a shared centrally managed VPC. In this model, the account that owns the VPC shares one or more subnets with other accounts called the participants that belong to the same organization. After a subnet is shared, participants can view, create, modify, and delete their application resources in the subnets that are shared with them. A VPC peering connection enables you to privately route traffic between two VPCs. Instances in either VPC can communicate with each other as if they were on the same network. You can create a VPC peering connection between your own VPCs with a VPC in another AWS account or with a VPC in a different AWS region. When you set up the VPC peering connection, you create rules in your route table to allow the VPCs to communicate with each other through the peering resource. For example, suppose that you have two VPCs. In the route table for VPC A, you set the definition to be the IP address of VPC B and the target to be the peering resource ID. In the route table for VPC B, you set the destination to be the IP address of VPC A and the target to be the peering resource ID. VPC peering has some restrictions. First, the IP address ranges cannot overlap. Second, you can only have one peering resource between the same two VPCs. Third, transit peering is not supported. This means the traffic from a VPC goes to the second VPC and it stops there. It cannot go to a third VPC. By default, instances that you launch into an Amazon VPC cannot communicate with your own remote network. You can enable access to your remote network from your VPC by attaching a virtual private gateway to the VPC, creating a custom route table, updating your security group rules, creating an AWS site-to-site VPN connection, and configuring routing to pass through traffic to the connection. One of the challenges of network communication is network performance. Performance can be negatively affected if your data center is located far away from your AWS region. For such situations, AWS offers AWS Direct Connect. AWS Direct Connect enables you to establish a dedicated private connection between your network and one of the Direct Connect locations. This private connection can increase bandwidth, throughput, and provide a more consistent network experience than internet-based connections or VPN connections. Direct Connect uses Open Standard 802.1q virtual local area networks. On occasion, you will need to connect VPC resources to AWS regional services like Amazon S3 and DynamoDB. A VPC endpoint is a virtual device that enables you to privately connect your VPC to these supported AWS services. A VPC gateway endpoint is a gateway that you specify as a target for a route in your route table for traffic destined to either Amazon S3 or Amazon DynamoDB. Traffic between your VPC and these services does not leave the Amazon network, so it remains private. More recently, AWS has introduced AWS Private Link. It requires a VPC interface endpoint. AWS Private Link simplifies the security of data shared with cloud-based applications by eliminating the exposure of data to the public internet. AWS Private Link provides private connectivity between VPCs, AWS services, and on-premises applications. All traffic flows securely on the Amazon network. AWS Private Link makes it easy to connect services across different accounts and VPCs to significantly simplify network architecture. We have mentioned the idea of VPC peering to connect to VPCs. Consider how will you connect hundreds of VPCs together. Each VPC pair will require a dedicated VPC peering connection. The complexity of connectivity can become a heavy burden. A transit gateway is a network transit hub that you use to interconnect your virtual private clouds. You can also connect on-premises network. You can attach a VPC, AWS Direct Connect gateways, or VPN connections to a transit gateway. The topology becomes a hub and spoke, which reduces the number of connections required, the complexity to implement, and be able to maintain it. Thanks for watching. We'll see you in the next video. Welcome back. You can build security into your VPC architecture in several ways so that you have complete control over both incoming and outgoing traffic. In this section, you will learn about two Amazon VPC firewall options that you can use to secure your VPC. The first, security groups. The second, network access control lists. A security group acts as a virtual firewall that controls inbound and outbound traffic to and from your instance. Security groups act at the instance level, particularly the network interface card. And you can assign each instance in your VPC to a different set of security groups. You can think of a security group as a way to filter traffic to and from your instances. Security groups are the equivalent of firewalls for your EC2 instances. They contain rules to allow inbound traffic. By default, security groups are sealed shut. You then proceed to define the type of traffic that will be allowed. Security groups are stateful. We only concern ourselves with defining the inbound traffic rules. The outbound traffic is always allowed. The second firewall option is a network access control list. Network access control lists work at the subnet level and control traffic in and out of the subnet. You can set up network ACLs with rules that allow or deny. You can also specify ports and protocols. Each subnet in your VPC must be associated with a network ACL. If you don't explicitly associate a subnet with a network ACL, the default network ACL is used. You can associate a network ACL with multiple subnets. However, a subnet can only be associated with one network ACL. That means that a network ACL and a subnet relationship is a one-to-one relationship. A network ACL is stateless. It has separate inbound and outbound rules that require configuration. The table shows the default network ACL. It is wide open in order for you to have focus on security groups as your firewall protection mechanism. You can define a custom network ACL, and this will require that you define rules in numerical order and define both the inbound as well as the outbound traffic to be allowed. Network ACLs are stateless, which means that no information about a request is maintained after a request is processed. Let's summarize the differences between security groups and network ACLs. Security groups act at the instance level, and network ACLs act at the subnet level. Security groups support allow rules only, and network ACLs support both allow and deny rules. Security groups are stateful, and network ACLs are stateless. For security groups, all rules are evaluated before a decision is made to allow traffic. For network ACLs, rules are evaluated in number order until a match is found and traffic is either allowed or denied. Thanks for watching. We'll see you in the Welcome back. In this video, we will discuss the Amazon Route 53 service. DNS resolution is the process of translating an internal name to the corresponding IP address. The DNS protocol stands for Domain Name System, and it functions like a phone book where internet names are replaced for the IP addresses of the corresponding machines. Amazon Route 53 gives you the ability to register a domain name, such as yourcompany.com, and have the service handle the names and hosts related to that domain. Route 53 is highly available, scalable, fully compliant with IPv4 and IPv6 address. Amazon Route 53 supports several types of routing policies. They determine how it responds to name resolution queries. Simple routing lets you configure standard DNS records. With simple routing, you typically route traffic to a single resource, for example, a web server for your website. With weighted routing, you assign weights to resource record sets to specify the frequency with which different responses are served. You might want to use this capability to do A/B testing, also known as blue-green deployment. With a blue-green deployment, you send a small portion of traffic to a server where you made a software change in order to verify that it's all working. For example, you might send 99% of the traffic to a system A and 1% of the traffic to system B that actually have some small modifications implemented before rolling it into production. You can use latency-based routing when you want the response to arrive in the fastest way possible. Route 53 determines the fastest way to deliver a response. This does not always mean that the shortest path will be used, especially if that shortest path is saturated and slow. Geolocation routing lets you choose the resources that serve your traffic based on the geographic location of your users. Geolocation routing determines where the request has originated from in terms of geographic location, and it responds with the address of the closest point of access to your service. When you use geolocation routing, you can localize your content and present some or all of your website in the language of the geographic location of your users. You can also use geolocation routing to restrict distribution of content to only the geographic locations where you have distribution rights. Failover routing, or DNS failover, can be used to help detect an outage of your website and redirect users to an alternate location where your application is operating properly. Failover routing requires a health check to be configured. If the health check fails, the secondary address becomes and gets distributed. You can also combine any of the other routing options into a multi-value response. Here we see an example of multi-region deployment with geolocation. With Amazon Route 53, the user is automatically directed to the elastic load balancing that is closest to the user. Multi-region deployment of Route 53 enables latency-based routing to the region and load balancing routing to the next availability zone. Amazon Route 53 DNS failover enables you to improve the availability of your application that runs on AWS by configuring a backup and failover scenarios for your applications. It also enables highly available multi-region architectures on AWS, and it requires a health check in order to monitor the health and performance of your web applications, web servers, and other resources. Each health check that you create can monitor the health of a specified resource, such as a web server, the status of other health checks, and the status of an Amazon CloudWatch alarm. Here you see how DNS failover works in a typical architecture multi-tier web application. Route 53 passes traffic to a load balancer, which then distributes the traffic to a fleet of EC2 instances. To ensure high availability, you can create two DNS records for the host www with a routing policy of failover. The first record is called the primary, and it points to the load balancer for your web application. The second record is the secondary, and it points to a static web page hosted in a specific Amazon S3 bucket. That bucket is configured as a website. Route 53 health checks and makes sure that the primary site is available. If the health check fails, a static splash page will be distributed. The static page alerts customers that you are restoring service. Thanks for watching. We'll see you in the next video. Hello and welcome. This video will cover Amazon CloudFront. One of the challenges of network communication is network performance. When you browse to a website, your request is routed through different networks. The origin server stores the original version of the data, which is commonly high density, like images, songs, or even videos. The distance between the customer and the original data server significantly affects performance in the playback and user experience. Also, network latency happens to be different depending on the geographic location of your users. For this reason, a content delivery network is an essential part of a smooth user experience. Amazon CloudFront is a fast content delivery service that securely delivers data to customers at high transfer speeds. It also provides a developer-friendly environment. CloudFront delivers files to users over a global network of edge locations. It is different from traditional content delivery solutions because you can take advantage of high-performance content delivery without negotiated contracts, high prices, or minimum fees. Like other AWS services, Amazon CloudFront is a self-service offering with pay-as-you-go pricing. Amazon CloudFront relies on Route 53's geolocation routing. Basically, a customer makes a request, Route 53 finds out where the customer is located in the world, and it responds with the IP address of the edge location closest to that customer. CloudFront then obtains the data from where it normally lives and copies it to the edge location. Then, the customer's user experience begins. As data becomes stale, it is removed from the cache at the edge location in order to make room for new content. You can define the expiration of data in the cache using a time-to-live number. This defines the amount of time in which the data cache will remain valid. Thanks for watching. We'll see you in the next video.